Department of Nanoengineering at the Jacobs School of Engineering at the University of California, San Diego. Dr. Xu is currently working in the development of new materials and manufacturing methods on electronics, with focus on wearable ultrasound technology. So I'm really confident that we will find Dr. Xu's presentation to be both informative and inspiring. So without further ado, please join me in welcoming Dr. Sheng Xu. So thank you, Professor. You can start your presentation.
Sure. Can everybody hear me well?
Yes, Thiago?
Okay. Can you hear me well? Hello? Hello, everybody. Can you hear me? Yes, you can hear me?
Yes, Sheng, we can hear you well. That's fine. Yes, we can hear you very well. Thanks.
Okay, great. Thank you so much for the great opportunity and the kind introduction. My presentation is on this wearable ultrasound technology. And why are we interested in this wearable ultrasound technology, right? So what you're looking at here is a typical image showing a patient in a hospital nowadays. And obviously, this patient is connected by many wires. This is very cumbersome and very constraining the patient's mobility. And this also takes a lot of nurses' time to connect those wires, right? So this is very, very obtrusive. And also, this type of measurement is only available in the hospital. If you leave the hospital, you go back home, doctors have no idea what's going on. So you lose a lot of information, lose a lot of data. And sometimes when the patient is critically ill, then the doctors will have to order invasive procedures, such as the surgery, blood joints, so on and so forth. So, our vision is to develop a wearable patch like this. So this patch is, flexible, stretchable, like our skin. You can put this patch on the skin, at anywhere, anytime you want to do the measurement. So you can provide 24/7 continuous monitoring and does not lose any data. And, when this patient is critically ill, so, this patient even does not have to break up his or her skin. This device will have access to those deep tissues, central organs, right? So, how great is this? What you're looking at here is a video showing a patch that we can laminate on the chest and is sticking in a coil. This coil provides power. And when this device is powered up, then it can provide an EKG or heart rate variability wirelessly transmitted to those, laptop, cell phone, cloud, so on and so forth. So what you see here is the raw signal we can collect. You can already see those well-defined characteristics peaks, PQRST, as you would expect to see in those high-quality hospital measurements. The baseline shifted because there's a capacity in the circuit, so we have to provide this charge for the capacity before everything becomes stable. Well, wearables are very powerful, but it's only a single layer. So after we came to San Diego, we thought about maybe we can develop this multi-layered wearable device so that we can integrate more functions, more components within limited footprint. So what we're looking at here is the first multi-layered wearable ultrasound, a wearable we can integrate like 8 different sensors within the footprint of a stent, postage stamp. And what you're looking at here, those dashed lines are those, vias. Those different color of the vias connect different layers, right? These vias are pretty much like the elevators in the buildings. Elevators provide the people, provide, resources to different floors of the building. But the vias provide, electricity, provide, signal to different layers of the circuit, right? So this is the image of the 4-layer circuit. This is how it looks like after you finish all the fabrication. It's flexible, stretchable, so on and so forth. If you do a deep dive in the literature, you can find that there's so many wearables, and you can sense so many different things. Both those things, signals can be basically put into 2 categories: physical signals, chemical signals, right? There are lots of them, and I'm not going to go through the entire list because they're not my focus. Here, my focus is that those signals that can be measured by the existing wearables have a common limitation. They are limited to the skin surface, very shallow to the skin surface, right? However, there are lots of more signals beyond your skin surface in your central vasculature, musculoskeleton, cartilage and bones, tissue fluids, visible organs, right, like your heart, lung, kidneys, brain, so on and so forth. And the existing wearables can only capture signals here, on the skin surface. And then below the skin surface, there are a lot of more signals that those, wearables are yet to, tap into, right? So here's my hypothesis. My hypothesis is that those deep tissue signals have a strong and fast correlation to the disease, development and the status than those surface signals. They have a much powerful prediction, capability for those, adverse events, those, acute diseases. Then, how can we, access those, deep tissue signals, right? So we use ultrasound, and because the ultrasound is, biocompatible, it can penetrate our human body as if we see through skin, and it has been used in clinics for decades and demonstrated with lots of functions, right? So by taking the ultrasound, on this wearable platform, we can basically monitor what's going on in our deep tissue central organ. Ultrasound add a new sensing dimension to our, existing wearables. How about the other modalities, to ultrasound? Why do you choose ultrasound? So, my group published a review article about 1 year ago, trying to summarize all existing possible modalities that can sense those wearable, deep tissue signals. And there are 6 of them. Vibration sensing, neuroscience fluorescence, electromagnetic antenna, impedance tomography, and ultrasonography. We compared all those 6 different techniques in terms of 3 critical metrics: penetration depth, spatial resolution, and temporal resolution. Eventually, we find out that the ultrasound is our favorite because it provides a very wide range of penetration depth and also very high spatial resolution and fast enough temporal resolution so that we can capture those dynamic processes in the human body. So what you're looking at here is a schematic image showing a wearable ultrasound patch that we demonstrated about 5 years ago. So in this wearable ultrasound patch, there are like 100 transducers, 10 by 10 array. And each one of them is individually controlled to transmit and receive ultrasound. And these are multi-layered, as shown in this, exploded view of the device. And those images at the bottom shows how soft this wearable ultrasound patch is. It's flexible, stretchable, and it can be twisted, showing the mechanical reliability of this device. So what's the fundamental property, performance of this ultrasound device? Because we use this state-of-the-art transducer, so it has well-defined electromechanical properties with very clearly defined resonant and anti-resonant frequencies, and these 100 transducer elements have very consistent, similar frequencies, showing the reliability of the measurement. The crosstalk between those transducers are very, very low because we use ground-split composite, so the shear waves are like suppressed, and also we use those highly attenuating elastomers to isolate, to absorb any possible crosstalk between the transducers. Because of reliable mechanical design, so when we stretch this transducer to 50%, that's 1.5 times the length of its original length. It's still like it's reliable. It does not show any breakage or like a degradation, right? So this is the electromechanical curve. As you can see here, when we stretch it, from 10% to 40%, those curves does not shift, does not change, with consistent anti-resonant and resonant frequencies. So what do we do with this wearable ultrasound patch? We first thought about imaging on a flat surface, on a concave surface, on a convex surface. So you can see that there's a defect between below those surfaces, right? Why is this useful? This is useful for detecting those cracks, those fatigue in the flight engine, in the buildings, in the car, in the bridges, so on and so forth. So we can do this. This is so-called non-destructive examination, NDE. So this is the simulated shear wave, longitudinal wave, and those are the collected signals from the defect from the sample surface. And after we know the ultrasound velocity, we can locate the defect, position, accurately. Because there's a 2D array, so we can do 3D imaging in one shot. So this is the schematic showing two defects with non-parallel orientation, and this is the imaging result. In 3D, because the imaging result in 2D, it all match the schematic design almost perfectly. The most exciting thing about this technology is we can do those solve biomedical problems using these engineering solutions. We can apply them to the human body. So what you're looking at here, the image is showing how soft the patch is. You can compress it, twist it, and cover a really curved surface. And when you put this device on your neck, while skiing, you move around, does not constrain your motion, does not demand because of the self-adhesiveness of this device. So one of the biomedical problems we looked into, we first thought about this blood pressure. I'm sure hypertension is number one risk factor for cardiovascular disease, which kills more people than all cancers combined. So this is the operational scenario. We have a device in the neck, and there are two vessels, carotid artery and jugular vein. They provide perfusion to the brain, and this is the measurement mechanism. So basically, the ultrasound beam is transmitted into the human body, and you will experience two reflections from the anterior wall and the posterior wall. And as you can imagine, when your pulse comes in, your vessel wall will actually dilate class, right? So that means those reflection peaks will shift back and forth in position. So by monitoring the distance between those two reflection peaks, we are measuring the vessel diameter. Through a series of well-established equation and the calibration, we can convert the vessel diameter into blood pressure, and we can transmit 5,000 pulses every second in the human body. So we can record blood pressure waveform in a very high tempo resolution. So this is the waveform we can collect, and this is the waveform from the wearable ultrasound patch. This is the waveform we can collect from the commercial tonometer. You can see the close, proximity of the morphology and the numbers after calibration. An advantage of this wearable patch is you can laminate this device on a curved surface, even without gel. And this is because this packaging material has a very intimate conformal contact with the skin surface because of the similar softness, the similar stiffness of those packaging materials to human skin. So this is the measurement of the blood pressure waveform with gel and without gel. You can see the close proximity of the quality. By integrating with the ultrasound patch with the electrochemical sensor, we can sense those chemical and physical signals simultaneously on one device. So this is the measurement schematics, so that we can have a holistic view of what's going on in the human body in the metabolic and hemodynamic system. After you drinking, eating, exercising, all kinds of daily activities, right? So this is a video showing the Congress, hearing. I'm not sure you know how much you know about the Congress hearing. Basically, this is the time when these federal agency directors use our research results as a testament to show the impact and the importance of the National Institutes of Health funding. So if you're interested, you can go to this video, this link to watch this video. Because you cannot hear sound here, so I will not play this video, so save some time. So ultrasound is a platform technology, and it has many powerful capabilities. One powerful capability is so-called phase array. So if you do not know what is a phase array, it's basically a technique by controlling the timing of activating those transducer elements, then the ultrasound beam can be focused and steered to an angle. Right? So for example, if you activate all those transducers simultaneously, then the beam will be focused somewhat directly on the missed device. If you activate this guy first, this guy last, then the ultrasound beam will be focused and steered somewhat to the right, right? So this is the phase array control mechanism, and this is the phase array. So as you can see here, this phase array is much larger and denser than the previous ultrasound device I showed you. It's 12 by 12 array and 144 elements, because we want to transmit more ultrasound energy in the human body that can penetrate deeper. The second thing is that the distance between the elements are smaller, because we want to minimize the so-called side lobe, grating lobe, to minimize those artifacts. The third thing is that we have used low frequency 2 megahertz in comparison with the 7.5 megahertz in the previous case. And these two methods can enhance the insensitivity of this device to morphology deformation. What does that mean? I will, show you in the next few slides. So a good question you may ask is, well, the phase array requires activating the transducers with a certain delay profile. But what if you, deform your phase array? Then you have to adjust your delay profile, right? So if you do not know, how your phase array is deformed, profile. So, this is a good question. It's a grand challenge in the field. Lots of people in the world are working on this, and they have already published quite a few, papers. I would say, those, solutions are great, but not perfect. So, how do you solve this problem? Well, we are still working on this. But before we reach a perfect solution, we find a, intermediate solution that allows us to go around this problem. So, what's the intermediate solution? So, what you're looking at here is a flat transducer on a plane surface. If you want to focus somewhat to the right, the blue bar is the time delay profile. That means you have to activate this guy first, this guy last, right? So the same transducer array, if it is on a curved surface with a curvature radius of 4 centimeters, then the yellow bar is the this so-called phase aberration correction you have to apply on top of this blue bar. As you can see here, average less than 5% of this blue bar, then that means we can safely ignore this yellow bar and just apply this blue bar on this curved transducer array as if they are on a flat surface, right? So they will hopefully achieve the same focus at the same location. So that was the idea, that was the hypothesis. And here the schematics you can see here when the transducer is on a planar surface, and when you apply a time delay profile, and this phase array is focused to the left with a tilting angle of 15 degrees. And when this transducer is on a curved surface with a curved radius of 4 centimeters, and we applied exactly the same time delay profile, and as you can see here, is focused, with a tilting angle exactly the same as if they are on a flat surface, right? So that proved our, hypothesis. That means we can just treat this curved transducer array as if it's on a flat surface. The reason why we can do this is because with low frequency, 2 methods have long wavelengths, a low frequency long wavelengths. So the long wavelengths enhance the insensitivity of this device to physical deformation. Well, what if you want to do more accurate informing to get a higher resolution, higher quality images? We can also use 3D camera to scan the skin morphology or whatever surface contour with very accurate location of the transducer array, so that we can apply those exact coordinates of each transducer element to the beamforming algorithm, so that we can get a better image results. So with that in mind, then we can start to use the phase array to measure a lot of things. So this is the image showing the variable phase array on the neck to measure blood flow, and this is the Doppler color Doppler image of the flow in the carotid. So this is the image showing this flow distribution. After all those angles, then we can calculate the numbers and get this spectrum Doppler. On the spectrum Doppler, you can identify those very critical parameters, such as end-diastolic velocity, peak systolic velocity, and those two numbers are what doctors are looking for to diagnose your heart conditions. So this is a measurement from the wearable ultrasound patch. This is the measurement from the commercial ultrasound equipment, and you can see the close proximity of those two measurements. And recently we demonstrated B-mode imaging, and as you know, B-mode imaging has been used in clinics or in many divisions in diagnosing, monitoring a lot of things, right? So this is what the cardiologists will do to monitor your heart. They typically use the 4 standard views: apical 4-chamber, apical 2-chamber, personal long axis, personal short axis views. So this is the schematics. This is imaging from the wearable patch. This is from the clinical image device. You can see the close quality of those two measurements. And what I want to focus is this so-called peristernal short axis views. That's the cross section, in this orientation. And you can imagine when you move this cross section along this direction, you got those different, views of the basal view, mid-cavity view, and the apical cavity view. And if you superimpose all those views together, you got those so-called 17-segment model, with each segment corresponds to one particular area in your myocardium. And why is this interesting? This allows you to monitor the beating of each segment in your myocardium so that you know which segment, which part of your myocardium has abnormality. This is called regional wall motion abnormality. And there have been clinical evidence to show that this regional wall motion abnormality is about half an hour earlier than those EKG to predict heart attack. So that can potentially save lots of lives. And after we know which regional myocardium has this beating abnormality, then we can know which segment of the coronary artery has blockage or stenosis or reduced blood flow. Then we can provide timely intervention to save people's lives. So this is a video showing how this ultrasound patch works. You can see that this is the student, this is the wearable ultrasound patch, this is the monitor, and in this device there are two arrays, two linear arrays, cluster arrays. They are orthogonal to each other. So that allows you to see two orthogonal independent views of the heart simultaneously. So this is simultaneous imaging without any dependence with each other. And you can see that when the student stands up doing some exercise, there's like no motion artifacts at all, right? That's because because of this intimate conformal integration of the wearable ultrasound patch with the skin surface. So when you move around, those motion artifacts are filtered. So with this, enable technology, then we can do lots of interesting things. One thing we came into our mind is called the stress echocardiogram. So basically, what the doctors will do is they image your heart before exercise and then put you to do some very intense exercise, and then after that they do some imaging of your heart again. So however, what is really critical is how your heart behaves during exercise, because lots of those risks are hidden. They do not show up until you put the maximum stress, maximum exertion onto the heart, right, onto the condition. So with our technology, you can continuously monitor before, during, and after exercise. Do not miss any critical moments. So those are the images of the B mode. You can see those are heart conditions, and those are the continuous M mode. You can identify lots of interesting features. Those look like noise, but they are signals of breathing, heart beating, valve motion, so on and so forth. So continuous imaging can produce lots of data, 30 frames every second. And if you show all those images to the doctor, they will be overwhelmed. So we developed a machine learning algorithm to automatically process those images. In this case, to segment the left ventricle volume from the apical portion of it. So by getting this left ventricle volume, then we can derive these three critical cardiac indexes, such as stroke volume, cardiac output, and ejection fraction. So this is the left ventricle volume waveform. Is very dense, and if you zoom in, you can see those waveforms of this left ventricle volume right after exercise. Some minutes after exercise, right? You can see the waveform apologies are very different. Some minutes after exercise, the heartbeat slows down, and the heart has more time to complete all those detailed processes. So that's why you can see those dichromatic notch. And from this left ventricle volume, you can derive this ejection fraction, stroke volume, cardiac output, and heart rate. Those waveforms are so valuable because in existing clinics, those doctors will have to use those casters, Swan-Gang casters, to do those measurements, and they can only measure one value every heartbeat, right, by those thermal diffusion techniques, and this is highly invasive. Here, with our technology, we can get like 30 measurements every heartbeat, and this is totally non-invasive. Ultrasound is a mechanical wave, so you can measure lots of mechanical properties of human tissue. And I'm sure you know that the biomechanics is related to lots of diseases such as cancer, fibrosis, aging, those cardiovascular disease, and this musculoskeletal injury, right? So this is the schematics of how to measure the those stiffness of the tissue. So basically, one transducer can emit a ultrasound beam, and the ultrasound will be reflected by those tissue interface, right? And if you compress this entire tissue, I'm sure you can imagine that some soft tissue will be compressed more, some rich tissue will be compressed less. So those interface, those peaks will be, shift, with different, degrees, right, different levels. So by correlating how much like each peak is shifting, then we know how soft this or how rigid this tissue layer is, right? And they are like a 2D array, so we can of this transducer, so you can form a 3D image. And this is testing on the phantom, B-mode imaging. You cannot really tell which layer is soft, which layer is stiff. And the displacement, strain, and the modulus, you can clearly identify, this is soft versus soft tissue. More phantom experiments shows different orientation. All those measurements match our expectation perfectly. So the student designed a experiment to showcase this continuous monitoring. So when he applied the stick in the lab and heating from the bottom, so those tissue will dehydrate, and when they dehydrate, they become stiffer. And when you heat from the bottom, so this stiff layer will grow right from to the top, right? So this is exactly what we could sense. You can see the bottom layer is like a stiffer, and this interface between soft and stiff layer is growing at constant time. So how do you know your measurements are accurate? So this is the 3D mapping of ultrasound. This is the 3D mapping of MRE, magnetic resonant elastography. You can see those tissue distribution are very close to each other, and even the numbers like so close to each other. They have some discrepancies because they are two different techniques. They have different frequency and they have different boundary conditions. So we apply this technology to monitor, human body where are very prone to those musculoskeletal injury, such as shoulder, forearm, thigh, and calf. And this is the imaging, B-mode along the depth. This is the elastography imaging along depth, showing the tissue stiffness. You can identify all those interesting anatomical structures. So what's the use case? We made a pretty nice demo, and this is so-called delayed onset of muscle soreness. Why is delayed? That's because sometimes when you do intense exercise, and if there's a muscle soreness like the day after or 2 days after, right? The delayed process is because a lot of very sophisticated metabolic process going on. But this soreness is actually this muscle fiber rupture is actually an injury. It's not a big deal for you, but for those soldiers in the battlefield, for those elite athletes, their performance is very critical. So we have to monitor their training process, training regimens, so that we can maximize their training outcome, prevent any injury. Otherwise, the performance is compromised. Then it's a big loss. So this is the experiments the student did, like. They did this essential exercise followed by national recovery, massage, and thermal treatment. So this is the period when they did this exercise, and this is the top. The top is the objective measurement of tissue stiffness. You can see that your muscle has already started to become stiffer, like a few minutes after exercise, 3 hours, 6 hours, 1 day, 2 days, so on and so forth. So at the bottom here, are the subjective feeling of the muscle soreness, right? So you can see that it do not feel much, and after 1 day, 2 days, and it peaks around the 3 days, right? So this is always like delayed. So with all technology, we can provide a timely feedback, in training performance and prevent any injury. So ultrasound is a physical waves. You can measure blood pressure, blood flow, tissue stiffness. You can form images. But how about chemicals? Lots of chemicals, molecules, reactions in the human body. How do you sense those things in the deep tissue, right? So this is done by a technique called photoacoustics. And if you don't know what it is, it's basically a technique by coupling light absorption and ultrasound imaging together. So we use a beam of light with certain wavelengths to shine into the human body. We use laser because laser has a strong intensity, can penetrate very deeply. So when these molecules absorb the light, they will be heated up, and when they heat up, they will swell. When they swell, we generate ultrasound. So the ultrasound can propagate to the skin surface and eventually picked up by those transducers, and then we can use those information from images. So this is the image of the photoacoustic device. You can see it's flexible, stretchable, and can be twisted. So those yellow squares are the lasers, VCSELs, vertical characters emitting laser. Those are the transducers. And we use 150 nanometers. You cannot receive the laser. It's IR, is infrared. And this is the IR camera image showing the device stretching, bending, twisting, showing the mechanical reliability. And why do we use 850 nanometer? That's because we can differentiate blood from the rest of the liquid, fat, water, milk, and plasma. So this is the beam of imaging of all those 5 different liquids. You cannot really tell because they have similar acoustic impedance. However, if you use the photoacoustic, you can detect the blood and differentiate blood from the rest of the 4 liquids. So what is this is because if you find 4 different liquids in the human breast cyst, then it's very normal health. But if you find the blood in the human breast cyst, then it's a strong indicator of breast cancer. And I'm sure you know breast cancer is the most common type of cancer in the world and is highly preventable, highly treatable if discovered early. So this type of device can empower the patients to do screening at home, to do more frequent diagnosis at home without frequent visit to the hospital. So that can encourage early diagnosis and improve the treatment outcome of saving lives. So this is the 3D imaging of the vessel in the human arm, and this vessel is about 1 centimeter below the skin surface in 3D. Those are the 2D slices of the imaging results, and this is the corresponding photoacoustic signal of those each image. And it turns out that the photoacoustic signals is linear proportional to the temperature. So we can use this photoacoustic signal to monitor the core body temperature. Why core body temperature? Because skin temperature is very susceptible to the room temperature, environment fluctuation, sweat conditions, and so forth. Core body temperature is more stable, is a more accurate reflection of your hemostasis, your metabolic rate, your inflammation, so on and so forth. So this is a fancy experiment showing the warm and cold region, and in the middle is a gradient, and we can map the gradient, the temperature gradient with the photoacoustic device. And we insert these two thermocouples at those 2 locations, 1 and 2, and we can see that the thermocouple measurements and the photoacoustic measurements overlap with each other very well, almost perfectly. So I want you to notice that the thermocouples are invasive, and you can only measure 2 points. Here, photoacoustic device is non-invasive, and you can do 2D, 3D mapping. So this is a totally different technology. So up to this point, you can see that we can make a very nice patch. But people ask me, how do you deliver power? How do you transmit the data? So this is the entire system. This is the patch. This is the flexible cable, and this flexible cable is connected to an adapter. This adapter will allow you to send the power and the data to this central processing station called Versonics. So this is how the entire system looks up. And recently, to eliminate this, flexible cable and this, central processing station, we designed this, flexible circuit that allows us to wirelessly interface this flexible patch and send the data to the, central station. And this circuit is low form factor, is about half of the size of the credit card, and is low power, so that some size of the battery can provide the power for 3 to 4 hours. And the critical challenge in this wearable, autonomous imaging is that when you put this patch on your body and you move around, your deep tissue, your central organ is actually displacing, is shifting. So the student did this, experiment. When he put this patch on his neck, he rotated his head from -80 all the way to +80. As you can see here, this carotid artery actually shifts, right? Actually displaced with a displacement of 1 to 2 centimeters. So this is huge. And only when this carotid artery is directly underneath the patch can you get this, measurement of this blood pressure waveform. And when you move away, you can not get anything, just this, a tissue interface vibration noise, right? So this is a motion artifact. And recently we demonstrated this AI algorithm that allows us to automatically recognize and track the moving target. so that we can select the best channel and output a continuous blood pressure waveform even during motion. Right? So this is all automatic, with this AI algorithm. Then the student did this demo by putting his patch in the neck, and when he moved his head around, you can see that obviously his carotid arteries is shifting, and this is the measurement result. The top three curves are the IMU data, electromagnetic moment unit, measurement of the head motion. So in the middle is this blood pressure waveform, and at the bottom is the heart rate, waveform. As we can see here, those 4 critical moments, right, when he, made this motion, and you can see here, this, during head motion, the blood pressure waveform is continuous, right? It does not have any disruption at all. So people will ask me, well, there are lots of low form factor, portable ultrasound systems already, such as the POCUS, point of care ultrasound, right? So how do you compare your technology with this POCUS, point of care ultrasound? So I would say POCUS is very powerful and it can provide lots of capabilities already, but they still have a limitation. The first is still manual. It requires an experienced user to use it well, and that experienced user needs a lot of training practice to apply those, ultrasound probe at different location, different angle, apply different pressure to get the best result, right? And different people have different results. This is so-called operator dependency, and sometimes you can get even wrong or inaccurate measurements. And because of the need for a ultrasonographer, this measurement is expensive. One ultrasonographer is taking care of 200 patients in those low middle income countries. So because of the need of those people, manual holding is only one-time testing, and this type of measurement usually happens in the hospital only. So you can only get this snapshot of what's going on in the body, and the patient has to remain stationary. And this measurement only has to require gel, right, because of this air bubble, right? So with our wearable on the head, this is hands-free, just slap it on, and this electronics will do scanning, the AI algorithm will do this data interpretation, and it empowers a general user to use this technology to monitor their health and diseases. So it lowers down the barrier of adopting this technology. Therefore, you took those ultrasonographer out of the picture, is operator independent, and this is low cost, right? So because everybody can use it, and it requires minimum training. And this device is continuous. We can do this monitoring at any time, anywhere. It can provide a comprehensive, data acquisition and interpretation. And most importantly, this type of measurement can enable motion. You can add stress to this entire measurement, right? So you can do a lot of things with this technology. And this is gel-free, so it creates it does not have the problem of disinfection. So with that, I would like to conclude by acknowledging my group. I'm learning from them every day, and my critical collaborators and also the funding agency. The size of the logo is roughly proportional to the amount of funding I accumulated over the years. So finally, I want to make an announcement that I'm constantly recruiting postdocs and grad students in any fields related to ultrasound, materials fabrication, transducers, hardware, circuits, control systems, signal imaging processing, so on and so forth. If you're interested, you are welcome to send your CV to the email address. Thank you very much.
Thank you so much, Dr. Xu. This was amazing talk. I learned a lot. I have we're open to questions now. Is that okay?
Sure.
Okay. So I will start with one question, and is the ultrasound, one of the problems of the ultrasound is the body fat. So some people with obesity, they have some problems with how deep the probe can get, right, and the tissue. So I have seen that you always use in places of the body that don't have much body fat. So why do you have to talk about it? How is it a problem in your case, in your devices?
Well, that's the same problem. Fat, as you know, this adipose tissue has strong absorption attenuation to ultrasound. We have the same issue. I would say the only thing we can do is to crank up power and increase voltage so that it can penetrate deeper. That's the only thing we can do. But conventionally, you have to press very hard to squeeze this fat away. But in our case, we cannot do this. It's all slapped on, so you just have to run it out. Yeah.
Okay, thank you. We have a question from the audience. Let me read for you. It's could you elaborate on the mechanism employed for signal transmission from the wearable ultrasound device sensor to facilitate real-time image formation? Specifically, how does the device ensure efficient and reliable data transmission while maintaining high resolution imaging capabilities?
I'm sorry, the internet here is kind of unstable. Your voice is kind of cut off. Can you repeat the question?
Okay. So it's a big question. So let me find a way to summarize it. So the person is asking for you to elaborate on the mechanism for signal transmission from the wearable device sensor, the ultrasound device, to facilitate real-time image formation. And how do you get high resolution imaging?
Oh, that's a very complicated question. But yeah, that's a very good question. In a nutshell, we use this beamforming. I'm not sure how much you know about beamforming. Basically, we transmit those ultrasound beam to the transducer into the body, and then we use each one of these transducers to acquire those refracted waves. And then we put a timestamp on those refracted waves, and then we do beamforming to do image reconstruction to form those images. And there are lots of ways to do beamforming: plane wave, focused wave, divergent wave, confounding wave. Lots of ways to polish the imaging quality. But you also have to balance the imaging quality and the frame rate. Sometimes if your imaging quality is good, but your frame rate is low, then that means you have freezing images. That's not reflection as fast. So that's the trade-off you have to make. Yeah, good question.
Okay, thank you. So Federico, would you like to ask the next question?
Sure. If I'm able to translate correctly, Sheng, we have a question from the audience. If other wavelengths other than 830 nanometers were tested, this is what I got. I hope that I translated correctly.
You mean the wavelength of the ultrasound or the wavelength of the light?
This is a good question for who made this question. So I'm sorry about that.
Yeah.
No, I think
it was not very clear.
It's for the chemical sensor, check for chemical like lactate, uric acid. And the person is concerned if you use another other than 830 nanometers to get other to find out other chemical devices, chemical.
Yes,
substance.
yes, that's a beautiful question, I would say. We are actually working on now trying to use different wavelengths to sense different molecules. I'm sure you know each molecule have their own signature absorption, right? So you just have to find the sweet spot for that molecule so that they can selectively detect that molecule. So that's a trick thing. And most of the time, one wavelength, one light source is not sufficient. You have to choose a multiple. And the ideal case is use 100, 200 wavelengths. And therefore you got those, so-called spectroscopy, right? And, each molecule have a very different, fingerprint absorption in the spectroscopy. So that's, the ongoing project in our group right now.
Okay, thank you. We have another question. Is there a time limit when you use it on your body, on the surface of your body? I think the person is concerned about because we have sweats and the temperature increases, does this affect the time that you can use the device?
Well, good question. There are two aspects to answer this question. The first aspect is the compatibility with the skin surface, right? As you mentioned, the skin will have sweat, and the skin is constantly defoliating the dead cells. So that's why we have to take shower, either every day or on a regular basis, right? So basically, those showering can help you remove those dead cells, right? And those dead cells can delaminate your device, make your device like non-adhesive anymore, right? So there is like time limit in that regard. Sweating is another thing. This device, unfortunately, this patch is not like a moisture permeable. The sweat will accumulate underneath the device. So that's one limitation. Another aspect to address this question is how is the device compatible with the skin in terms of temperature, right? Because as you can imagine, when we apply lots of power to the device, it can, generate lots of heat, right? So what you're looking at here in this image, which I do not have time to go through, is a thermal camera imaging of the device after we operate for an hour. You can see the temperature rise to 36 Celsius degrees and then stabilizes, does not increase anymore. Even you increase the operation time. That's because this temperature reaches a thermal thermal steady state. The heat it generates and the heat dissipates into the environment become equilibrium, right? So that's why it stabilizes at the 36 and does not hurt yourself, does not burn you.
Thank you so much. We have another question here, and thank you for the presentation. Congratulations on your truly amazing work. What are your expectations for when these ultrasonic wearable devices you have shown us will begin to be commercialized? And what are the current roadblocks in this direction?
Well, very good question. I'm now doing a commercialization at this moment. So as you can see here, I do have some disclaimers. I have two companies trying to commercialize this technology, and hopefully in the next 2 to 3 years, we can have a product that we can sell or we can distribute to those end users, right? And the roadblockers are multifold. It's a total different world, and the challenges are in multiple aspects. Regulatory, reimbursement, right, manufacturing, and the distribution, right. So those are all like the things that I need to learn. I'm a technologist, so I come from a different background, and I had to build a team to work on this. Yeah, very good question.
Sheng, may I ask you a question before letting you go? I know that you've got to go, so we don't want to keep you around for too long. I don't want to oversimplify, but I'm really curious about your trajectory in all of your research up to this point. And I chatted a bit about this with your students, so I kind of know what the main issues are. But let's say there are three main problems that you have been facing with all this research, right? One is a biomaterial problem, right?
Mm-hmm.
One is signal processing problem.
Mm-hmm.
One is the problem of battery, right?
Mm-hmm.
What do you think has really been so far the hardest challenge? And correct me if I'm wrong, this should be the three main axes of your research, right? But if there's an additional main problem, please correct me. I see these three as the main ones from the outside.
Well, very good summary. I would say the most challenging problem out of the three you just mentioned is the battery. Because the ultrasound is truly power hungry. You have to launch those waves, real waves, into the human body, right? And as Professor Fabio mentioned, if people have this really thick fat layer, you need more power. So battery is now the bottleneck. And for the image I just showed you, this battery, can only last, 3 to 4 hours. So if we want to monitor for one day, we have to, recharge it or like change the battery, or we have to do something like called duty cycle, so that we don't measure those blood pressure or whatever signals, continuously. We measure it once every minute or once every 2 minutes, something like that.
Great. Fabio, I think we can probably wrap this up, right? I don't think we have other questions, and I will let you close. But first of all, let me thank Sheng again for accepting our invitation. I was really honored that you were with us today.
Yeah, thank you.
Thank you so much. Yeah, thank you so much, Federico, Professor Federico, Professor Fabio, for giving me this wonderful opportunity. Thank you very much.
Pleasure was mine. Yeah, thank you.
Okay, safe travels, and see you some other time. Bye-bye. Thanks.
Sure. Bye, everybody. Thank you very much, everybody. Bye.
Bye.